Cycle 1, Lesson 9, the inverse. The inverse of a function undoes the original function. In other words, it's the opposite of a function. By undoes, I mean it takes the opposite order of operations. So if a function has multiply, we're going to divide. If it has add, we're going to have subtract. If it has squaring, we're going to square root. And we're going to do it in the opposite order, much like we would think about solving an equation. Think about isolating a variable to solve an equation. Only instead of isolating a variable, we're just coming up with a new function that does it all for us. We represent an inverse function with this f at -1. So when you see a -1 exponent like this, that's going to indicate inverse. So let's just look at an example. Determine the inverse of the function f at x equals 2x minus 5. So 2x minus 5 means you take some number, the x stands for a variable, can be a different number. I multiply by 2, and then I subtract 5. That's exactly what this diagram is showing. We start with a number, and then we multiply it by 2, which is what that 2x tells us to do, and then we subtract 5, which is what that part's telling us to do. And once we've done those things, we get our y value. So for example, if x was 3, if we multiply x times 3, x 3 times 2 for this function, we get 6. And then we subtract 5, and we get our output, which is 1. So in other words, if x is 3, y equals 1. That's what a regular function does. The inverse is just working backwards. So instead of starting with x and going to get y, it's like I'm starting with y and then working backwards to get x. So I'm going to do the opposite operations in the opposite order. So I'm going to start with f at x. If I was to work backwards from this one, going this way, going backwards, the first thing I'd get to would be the subtract 5. But I'm doing everything opposite. So I'm not just going to subtract 5, I'm going to add 5 to do the opposite. So add 5. And then the next thing I'd get to is multiply by 2. So the opposite of that is divide by 2. And then when I've done both those things, I'm going to get back to my original x value. So if I was to start with the number 1, if I add 5 to that, 1 plus 5 is going to give me 6. 6 divided by 2 is equal to 3. And that is the number I started with over here when I started this. So the inverse is the opposite of a function. So if I want to write this as an equation, f at -1, or f to the -1 of x, if I want to write it as an equation, I would start by adding 5, and I'd divide by 2. So this would be the inverse of this. So again, f at x is my regular function, or just represents a function, 2x minus 5 in this case. F with the -1 telling me about the inverse, and it's the opposite operations, but also in the opposite order. Fill in the table of values for these two different things. Okay, so for f at x equals 2x minus 5, I'm going to fill in this table here. So when x equals 1, 2 times 1 is 2, minus 5 is -3. So I'm just plugging different x values in here into the equation. So 2 times 1 minus 5. 2 times 2 minus 5 is -1. 2 times 3 minus 5 is +1. 2 times 4 minus 5 is 3. So there's a table of values. If I do this function, I'll just highlight this one in blue, so I'm going to fill the inverse table in this equation. So if I start with -3, then I'll put -3 in for x here. So -3 plus 5 is 2. 2 divided by 2 is 1, and my output is 1. If I put -1 in for x, -1 plus 5 is 4. 4 divided by 2 is 2, I get 2. 1 plus 5 divided by 2 is 3. 3 plus 5 divided by 2 is 4. What do you notice? X and y, these are like my y values, right? F at x and this is also like my y value here. F to the exponent -1, that's also just my output. They're the equivalent of my y values. So sometimes I'll refer to them as y values. So what do you notice? X and y for the two tables are reversed, or they're opposite. So I don't mean that they've switched places. I mean that if you say, just pick any number, so say 2, -1. If I go and look over here at a corresponding table or a row on this table here, x and y is reversed. So 2, -1 became 1, -2. And pick another one, 4, 3 became 3, 4. So they're reversed, they're opposites. So that's another feature of inverses. The table of values, the x and y coordinates get reversed for an inverse compared to an original function. So if a point xy is on a particular function, then the point yx will be on the inverse function. Reverse the coordinates, as I was just mentioning. So that comes in handy to let us graph inverse functions. So say we have a function f at x represented by -1, 1, 0, 2, 1, 2, and so on. So I'll graph that. I'll just put those ordered pairs on the Cartesian plane. So those are my 4 points as shown in the highlighted yellow. So what's the inverse? Well, the ordered pairs for the inverse, let's just write those out, and I'll do that in red here. So the inverse, I'm going to switch the x and y's. So -1, 1 becomes 1, -1, and 0, 2 becomes 2, 0, and so on. So those are my 4 points with the x and y coordinates reversed. So 1, -1 is down here. 2, 0 is here. 2, 1 is here. And 1, 2 is here. So those last 2 points I did were on top of the ones that were already there. Just they happen to coincide. There's no connection necessarily between them. Is the relationship a function? Well, yes, the original equation is a function. So f at x is a function. Is the inverse a function? No. F to the -1 at x is not a function because it fails the vertical line test. Right? If I could draw a vertical line through here or a vertical line through here. There's 2 outputs for one x value on the inverse. So the inverse is not always going to be a function just because the original graph is a function. When you switch those x and y's, sometimes you're going to get things that aren't functions. What do you notice about the graph of the inverse compared to the original? Well, it's the same shape, but it's like it's turned sideways. What's actually happened is it's been reflected. Imagine that I have a mirror or something that's going to reflect a graph on the line y equals x. So that diagonal line through the origin, if I were to take, again, all of my original blue points, if I took all those 4 blue points and flipped them over that line, I would get the red points. So this point flipped over the line became this point. This point flipped over the line became this point. The blue point became this point, and this blue point became this point. So the arrows are going from blue points to red points, and in every case, it's just them flipped over the line. So they're all reflected in this line y equals x. To determine the equation of the inverse of a function, we've seen that reversing x and y seems to be the common theme for inverse functions. So we can do the same thing with the equation. We can reverse x and y in an equation, and then resolve it for y, and we'll have our inverse equation. We just remember that f at x and y really mean the same thing. So to determine the inverse of this equation here, f at x equals 7x plus 2. Okay, so first of all, let's just replace that f at x with a y, because we know it means the same thing, and we're used to using that. So we're going to reverse x and y, right? That's the key. So my first step in getting the inverse equation is I'm going to put an x in for where y was. I'm going to put y in for where x was. And now I'm going to rearrange this to get y isolated again. So I got to get y by itself. So solving this equation and rearranging it, the first thing I do is I'd subtract 2 from both sides. Next thing I do is I divide both sides by 7. Now y is by itself, and I would rewrite it using function notation. Because this is the inverse of f at x, I do f negative 1 at x equals x minus 2 over 7. These two equations are inverses of each other. Again, they undo each other. So determine the following for the equation up above. So f at 1 means put 1 in for x in the first equation. So 7 times 1 plus 2, which gives me 9. Put f at 1 into the second equation. So f to the negative 1 of 1, it would be 1 minus 2 over 7. So 1 minus 2 is negative 1 divided by 7 is negative 1/7. As you can see, we don't get the exact same answer when we plug numbers into our function its inverse. There's no connection as far as that goes, and we just have to treat each one like its own equation. Looking at the graph, well, I guess we're going to do the graph in B part. Let's start by getting the function first. So what have we done? We've seen that we're going to switch x and y. So we're taking this equation where f at x is y. So I'll start with y equals 4x minus 3. I'll switch x and y. So x equals 4y minus 3. I'll try to solve it for y. So I'll add 3 to both sides. I'll divide both sides by 4. Y is by itself. I'll rewrite it in function notation, and I've got f to the negative 1 of x plus equals x plus 3 over 4. So there's my inverse equation. There's my original equation. Let's graph them both. So f at x equals 4x minus 3. That's just in this format y equals mx plus b, so it's got a y-intercept at negative 3. And it's got a slope of 4 over 1. So I'll go up 4 and over 1, up 4 and over 1. And then I'll draw my line through that. So that's this graph here. This one, the inverse, it'd probably be a little easier to graph if I were to put it into slope y-intercept form. So I'm going to rewrite the inverse function. I'm just going to divide, I'm going to break this into 2 fractions. So I'll divide it into 1/4 x plus 3/4. That's the same thing. It's just that I've broken it into 2 separate fractions. I can see that the y-intercept is 3/4, which would be about here, right? There's my y-intercept there. My slope is 1 over 4, so I'd go up 1 and 4 to the right, which would take me here. And then I've run out of room. But I can, that's enough to connect the dots. I can draw my line like this. And I guess it would be about like that. So there is my graph of the inverse. Again, the whole graph is reflected in the line y equals x. All right, if you picked any point on this line, on the original function, and reflected in the line y equals x, say I picked this point here, this one I'm doing in blue. If I reflect that, that's the point 2, 4, that would reflect to the point, 2, 5, that would reflect to the point 5, 2, which you can see I've got here. Or if I took this point here, which is 0, 3, negative 3, that would reflect to negative 3, 0. My line's a little bit off, as you can see. It should be going through negative 3, 0. So I missed the mark a little bit. But when it's drawn absolutely accurately, they are exact reflections. And point by point along my original line, my original green line, if I reflect them in the line y equals x, I get the graph of my inverse function. Okay, so let's just put this together and do some stuff with the equation. So f at x, for f at x equals 2x plus 9, we're going to determine the following. We're going to find out what f at 7 is. Well, that just means I put 7 in for x, as we learned many lessons ago now. That's how function notation works. Plug in the number for x and see what you get for your y value. 2 times 7 is 14, plus 9 is 23. Put in 5 for x. 2 times 5 plus 9 is equal to 19. This one is kind of interesting. If you look at this, it may look familiar. It is like doing y2 minus y1 over x2 minus x1, right? So if you think of 7 being an x value, then f at 7 is just the y value that goes with it. That would be an ordered pair. If you think of 5 as being an x value, then f at 5 would be the y value that goes with it. So really, this is just calculating the slope based on this original question. Pardon me, the phone just rang for a second, but I muffled it. All right, so f at 7 we saw was 23. And f at 5 was 19. That's just from what we did in parts A and B. Over 7 minus 5. So 23 minus 19 is 4. 7 minus 5 is 2. And I get a value of 2. And again, is that my slope? Well, yeah, it is my slope, right? If you look back at the original equation, 2x plus 9, my slope is 2. So that makes sense. For D part, we're supposed to find the inverse of f negative 1 at 7. So let's, just up here, we've got a bit of space. Let's find the inverse equation. So if the original equation is y equals 2x plus 9, if I switch x and y, I get x equals 2y plus 9. Again, if I try to isolate the y, I would subtract 9 from each side and then divide by 2. And then I'd rewrite it in function notation. So f to the negative 1 of x would equal x minus 9 over 2. And this would be my equation of my inverse. So that's what I'm going to use down here for D part. So I have 7 minus 9 divided by 2. 7 minus 9 is negative 2, divided by 2 is negative 1. F to the negative 1 of 5 would be, if I put 5 into my inverse function, so then it would be 5 minus 9 divided by 2, which is negative 4 over 2, or negative 2. And F part is really doing the exact same thing. It's also using, just finding the slope, really, of the inverse function. And I've already figured out in D, parts D and E, what f to the negative 1 of 7 and f to the negative 1 of 5 are. They're simply negative 1 and negative 2. There's a minus built into this function, of course, so I have to have this extra negative sign in the middle. Over 7 minus 5. So that's negative 1 plus 2 when I simplify the signs, which is 1 over 2. So I got this slope of 1/2. Does that match what we have up above? Well, remember, this original inverse function is not written in slope y-intercept form. If I was to rewrite it in slope y-intercept form to break it into two fractions, it would be the same as 1/2 x minus 9 over 2. So my slope would be 1/2, which is, again, what I got for the slope down below. So that's just playing with the inverse a little bit. The main thing that you need to take away from this lesson is that the inverse undoes an original function, and it does it by doing the opposite operations in the opposite order. And when you do that, what's going to end up happening, whether you're working with the equation or the graph or a table of values is that the x and y are going to switch places for all of them.